Yes, we're back. Welcome, Geomaticsday 2020. We're going to continue now with the video of the students of geomatics. The video is on the 3D noise simulation based on advanced input data using automatically generated TINs. And it's a project in collaboration with Rijkswaterstaat and RIVM. Mels, press the button and we can play the music. No, the video.
Welcome to the Synthesis project presentation of the 3D noise modeling team. Our team consists of Constantijn, Dennis, Laurens, Nadine and myself Marit. In collaboration with RIVM, Rijkswaterstaat and the TU Delft, we have developed a proof of concept to automatically extract a noise map directly from a triangulated irregular network, which is freely available. We have really liked this project and its outcome. We hope you do too. To model noise, a digital representation of the terrain is used. Currently, height lines are used to represent the terrain. These lines are three-dimensional lines representing high and low points in the terrain, not to be confused with isolines. These lines, however, partially require manual processing and are not as accurate as a tin. Our goal was to see if it was possible to directly use a tin representation of a digital terrain to find noise levels. Our hypothesis is that using a tin directly allows for automated 3D noise modeling according to the guidelines of Knossos EU. Nevertheless, this was never tested because existing software cannot take the tin as an input. In this presentation, we will first explain our inputs, how our algorithm works, then we present our results and discuss them in comparison with the current Dutch method. At last, we will go into the setbacks and limitations of our product and finally answer the research question. And now Laurens is going to talk about the algorithm.
Thank you, Marit. Our main input is a digital terrain model consisting of a triangle irregular network, also called a tin. Each 2D vertex has a height value and can therefore be lifted up to that height. As there can be only one vertex on a unique 2D location, vertical surfaces cannot exist. This is so-called 2.5D. We also use a building dataset of LOD level 1.2 or 1.3, which is based upon the BAG, Building and Address Dataset. An LOD 1.3 means that a building can have different roof heights, however, the roofs are all flat. This buildings dataset is merged with a ground type dataset to provide semantic information to our tin. This data stores the material and the building height. The material can either be absorbing or reflecting. In order to simplify the process of getting a cross-section from the tin, we decided it was best to make the tin constrained to the buildings and the ground type polygons. During the project, this has become the replacement for the ground tin. At last, the algorithm also requires a set of roads, which represent noise sources, and a list of receivers, which represent the locations of interest. Our client requested us to use a method where we search for the intersection point between 2 km long rays coming from the receiver with a 2-degree interval and the road elements, as can be seen in the slide. The length of the rays is specified in the European Standard for Noise Modeling. Using these source-receiver pairs, we can find the different propagation paths, either direct or reflecting. For reflecting paths, our algorithm currently supports single reflection paths, also called first-order reflection paths. These are the most commonly found propagation paths and make up most of the noise. We have also developed second-order reflections, but the noise contribution did not overcome the increased running time. Therefore, we have not implemented it. The first-order reflections need to be validated. For that, we use two tests. The first test verifies that the size of the building is sufficient to actually cause a reflection. This is done by checking whether rotating the ray by 1 degree in both directions still intersects the same building. When this is the case, the reflection has passed this test, as can be seen in the slide. The second test looks at the relative height in the case of buildings with common walls. The reflection is only valid when the reflecting building is at least 1 meter higher than the adjacent building, as can be seen on the right side. From these propagation paths, consisting of the source, receiver, and optionally the reflection point, we extract the cross-section by walking over the constrained tin. During this walk, we store the intersection points and add building roofs when encountering a building. This results in a vertical cross-section of the digital surface model, which consists not only of the terrain, but also the buildings. For each vertex, the material properties are stored. For one receiver, this is how these cross-sections look. As can be seen, a single receiver can create a lot of paths. Computing this for a grid of receivers quickly becomes computationally expensive. To make sure the computed paths are actually correct, we first visually checked whether the surface was accurately followed. From this side view, it can be clearly seen that the cross-sections follow the surface accurately. Secondly, we also tested the validity of the path with the noise computation software, which does several checks before computing the noise level. And now, Marit will talk about the quality of these results.
Thank you, Laurens. To verify the results of our method, we compare the results with those from our client. As this is to test and verify our concept, the client used the same input as much as possible. The terrain, buildings, ground types, sources, and receiver points are the same. We set up two scenarios, one with no reflections but significant height differences in the terrain, and another scenario with buildings and thus reflections. Let's start by comparing the scenario with no reflections. Looking at the images, they show that the noise results are very similar. There are three differences that we found between the noise results produced by RIVM and by us. First of all, our noise results showed more local minima and maxima, while the results produced by RIVM are more gradual. Besides, the noise results by RIVM showed lower noise levels further away, while our noise results showed lower noise levels in absorbing areas. Finally, our noise results are more prone to height differences. For a more quantitative comparison, a relative difference noise map and a histogram showing how each pixel in our approach deviates from the RIVM approach are shown. The majority of the pixels are within plus or minus 1 decibel from zero. This could mostly be attributed to the extra details provided by the tin. Now let's compare the results when reflections are added. Both methods present the same distribution of sound levels. Both approaches also show noise contour lines pulled towards the buildings where reflections exist, which means higher noise levels near buildings. Looking at relative differences, we can see that in flat reflecting areas, the RIVM model tends to have a lower noise level as we get further away from the source. But in the absorbing areas, the tested method tends to generate lower noise levels. The histogram shows that the majority of pixels are within plus or minus 1 decibel from the 1.5 decibel. The only major difference between the two scenarios are the introduction of reflections. These reflections could lead to such differences since a longer distance is traveled in reflections and the details from the tin could finally add up and create higher noise levels. We use different files in order to extract the propagation paths. However, these files can have a difference in precision, which in some cases cause a reflection to become invalid. We have tried to solve this by adding a tolerance, but this did not yet solve it and caused other topological inconsistencies. Therefore, it is not solved at the moment. This will in some cases cause slight errors when using incompatible input datasets. It could be solved by aligning the precision of the input datasets. Also, creating a constrained tin, incorporating the ground types and buildings have proven to be a challenge in specific cases. This sometimes resulted in an invalid terrain, as can be seen on the right side. Secondly, in the algorithm we created, direct and first-order reflections are taken care of. The test Knossel software handles the propagation paths that are vertically diffracted. However, horizontally diffracted and multi-order reflected paths are not considered. At last, we currently only support roads as noise sources, but in reality there are many more noise sources. For example, railways, the industry, and airplanes, which are not considered but can definitely contribute to noise pollution. we have successfully created noise maps, comparable to those produced by our clients, by directly using a tin model of the terrain. We know how several of the differences are caused and how they could be solved. The concept is therefore proven to be an interesting alternative to the currently used height lines. The main challenge was to make the concept compatible with many different situations, which was successful in most cases. Further improvements to this concept are the performance improvement by implanting it in C. This will allow the concept to use the test Knassas functions directly and remove writing and reading many files to the disk. Secondly, include support for other noise sources, adapting to speed limits and amount of traffic. Besides, support for diffracting paths as well as multi-order reflection paths. And finally, expand the support for other ground-type materials. While working on this topic, we also noticed other possible improvements for noise maps in general. First of all, create support for higher level of detail of buildings that include slanted roofs. Secondly, support not only 2D, but also 3D noise maps for high rises in urban environments. Finally, support for vegetation. We have really enjoyed this project and we hope you enjoyed listening to it. Cheers!
Super, yes. Well, thank you very much, Group RIVM, for this very nice presentation. There are several questions popping up. The first question is by Balazs Dukaray from Delft University of Technology. The question is, you encountered several issues with the input data, especially considering the original set of input. If you were to fix the data, where would you begin?
First I need to clarify something, that we have the input data that we got from for the project, and then we did something with the data to turn it into input data for our software, for our program. And the raw input data had invalid polygons. So first we needed to fix the invalid polygons. Sometimes polygons didn't have the value, so it had a value none of, let's say, like the building polygons would have a height of none, or it would have a roof level lower than the ground level, which meant it's an underground building. And we didn't need that for our program, so we had to clean that up as well. Or in the ground type data set, we had the polygons that didn't have an absorption index that we needed for the noise propagation. So that's the part with the raw input data. And then we had to overlap these data. And then we had the difference between the ground type and the building data set. And these differences gave sliver polygons or dangling segments, and that caused problems. And then we tried to fix them, but then we got a constraint tin that had a different precision with the building data set. So we also have to change the precision of the building data set to match the precision of the new constrained tin. So there were several things to fix for the input data.
Well, that's a very comprehensive answer to this question. Move on to the next question by Hugo. Did you interpolate the values, or did you calculate one value for each pixel? And then for the pixel, what resolution is this pixel?
Yes, the algorithm has as an output a set of points. We programmed them in such a way that there were a grid of receivers with a distance of 3 meters each from each other. So then we had to interpolate these values in order to get the map a continuous field. Among the two options that we have available in QGIS, we didn't program an algorithm for that. We used QGIS. We had a ID double and tin. We first tested with ID double, but it had some problems, especially because we had to determine a search radius for that, and it was producing some artifacts. So we opted for the tin, and the resolution was 0.1 meter for the raster pixel.
Very good. That answers all the questions. And next question by Jantien Stoter. also from Delft University of Technology. Do you think that thinning of the tin would be possible in a way that does decrease the computation time, but without significant impact on the quality of the noise simulation results? Who can answer that question?
I guess I can. Yeah, it's either me or Nadine. I don't know. I do know that right now that's pretty much our biggest, like, is where the biggest computational part of our program is going into right now, and it does it is the main source of our accuracy over the previous method. So at least in what I remember. So I wouldn't say that it would be easy to take out a lot of the tin, and you wouldn't want to do that because that's something that the tin actually provides is quite a bit of high accuracy. But saying that, there definitely could be it could be used to, like, you could definitely remove some of the tin, but it would definitely impact accuracy. Like, it does come hand in hand, so I don't think it's an easy trade-off there.
Okay, someone wants to add to that, or is the answer? Very good. Then we move on to the question by Peter van Oostrom. I'll just do individual persons, and everybody can ask one question. And if we have time left, then we move on to the next from someone that already asked a question. So Peter van Oostrom asks, you mentioned noise level at higher locations, for example, 2 or 3D floor balconies. Any clues how this fits into your method?
Yeah, I can answer that. So in the cross sections that we produce, we write them to an XML file, which is then processed by the test Knossel software. And in that file, you can address at which height the receiver is placed on top of the local grounds level. So normally we always do it at 2 meters height, which is the standard. But you can also set it at 6 meters or 10 meters height, and that will give you a different result.
Okay. Then a question by Yongliang Peng. Did you convert the tin to the noise map? Do all the pixels in the same triangle have the same noise value?
The conversion from the output, the points with the noise power values to the interpolation was actually the last part of our synthesis project, and it was meant to access the quality of the maps that we produced compared to the RIVM one. So we didn't get into much detail about the interpolation technique. We just opted to the tin as it was producing better results for that specific purposes, and then we produced the comparison. We didn't focus that much on why was a specific interpolation method better than the other one. It is important to notice that we took this approach because we wanted to compare pixel per pixel. In the noise community, these noise values are often shown as contour lines and not as an interpolation map. But we decided to do that because of the comparison that we wanted to do.
Okay, thank you very much. Then we have a question by Clara Garcia Sanchez. You mentioned further work by extending from 2D noise prediction to 3D. Do you expect the propagation of noise to behave in vertical direction the same way as in horizontal direction?
Yeah, in general, the sound has a lot of different ways of propagating, and the good thing about horizontal propagation is that there's usually a ground terrain below it, which will actually cause multiple reflections. So the sound ray itself can go in many various ways, and if there is an underground below it, then it will have various reflections along that underground. But if you have a vertical path, that could also work.
I'm not completely sure how Tasknossos deals that if you supply it in the same coordinate system, but for that we would have to ask one of the clients. Maybe they can answer it in the chat, but I think it's possible.
Yes, and just to complement, we used as our main literature the Knossos guidelines, and according to the guidelines, there are three conditions that we can work with, which are homogeneous, favorable, and unfavorable. This third one, the unfavorable one, is the one that you can actually think of sound going from up and down, as in like not going horizontally, but actually working in 3D. And we didn't work with that at all. It was our main goal in the synthesis project was the proof of concept of if it was possible to work with the tin. So this was not the most important aspect for this project, but it could be conceived as further implementation.
So your supervisor from RIVM, I think, responded there as well. A question I have myself, because in this project, of course, it was on the scientific part, let's say, on a research topic. But can you also say something about the social impact of your research? You can phrase it differently. Who's going to benefit from your research?
Yeah. So every 5 years in the EU, every country is asked to produce noise maps for its country. And these noise maps are used for various reasons. It can be to find out whether you can build a building somewhere, or do you need a noise barrier to restrain the sound coming from a road. So but it's used for more purposes than only that. You can also think about, do you want to place a highway throughout a natural forest or national park? What kind of impact would that have on the national park? Also, things like that can be considered.
Interesting,
yes.
yeah.
And if you think this theme is actually very interesting, because if you think of noise, you cannot visualize noise, nor you can touch noise, but it's still a very important factor in terms of the quality of the built environment. So I think that to answer your question, well, society in general gains a lot when you can actually map and access the quality of noise in our cities. And this is very useful for planning and urban design purposes.
Yes, fully agree. There's another question by Jantien Stoter. Let's take the second one. Let's say she posted on the chat in the chat. So, do you expect that adding more details to the building models, such as representation of roofs (LOD2), would indeed improve the results of the noise simulation?
The short answer is yeah. I'll say this real quick. The short answer is yes, it will. But the more complicated answer is that it will by such a small margin that it's probably not worth doing it, because when you're taking a look at an entire city, individual building facets are just not as relevant. If you're doing this on a small scale, then for sure. But on a citywide level, this is not a huge deal, unless you have big, outstanding like obstacles that have a major impact. But otherwise, no, not really.
Okay, so no improvement expected there. I get a final question by Jantien. You mentioned that no vegetation was considered. Is vegetation supported at all in the noise calculation methods? And if so, how is that being supported?
Yeah, it is supported in terms of material. So for each segment, so for each part in the cross section, you can supply it with a material, and there are 12 different default types of material, which go from raw asphalt, which is really reflecting, to very absorbing materials where they explain it can be considered like bushes or things like that. However, I believe it does not take into account For example, when you have trees, they are also quite tall. So they might be 10, 20 meters high, which also has another influence on the propagation there. And that is not taken into account. So the height of the vegetation cannot be added.
Okay, thank you very much. Well, that was the last question in the chat box. Let's say there's another question. It's a completely different question. But you work for a client or even two clients. How is that for you as students? That you were educated with some skills and competence in the Geomatics program. A lot of theory was provided, but how is it working with the client? You're all silent now.
Well, maybe I can respond. Yeah, I think it was really nice. It was really clear to us. It really became clear to us that our clients, Arnoud Kok from RIVM and Rob and René from RIVM and Rijkswaterstaat, they really know a lot about the noise and about how noise propagates and how to deal with certain situations. But on our side, so also our tutors, Jantien and Balas, they really know a lot about the data and the technical aspect of it. So that was a really nice match. And sometimes we had to explain something that was not completely clear to the clients, or how to implement that, or if something was easy, or if it would be really hard. But we could learn a lot from each other. So I think we all really enjoyed it.
Thank you very much. Well, I'll just see in the chat box I have to ask another question by Hugo, but let's make that one the last one. Wouldn't it be better to skip the tin and use a smart point cloud directly instead? A brief answer, please.
Well, I would say it depends on what the smart point cloud is, because we need to extract the cross sections, and we just, when we walk the tin, it's easier to know what is intersecting what. But when it's a point cloud, like if we miss a point, then how would we know what the cross section is? Or if we're missing an important building or something. So
yeah, so I think
that's a brief answer. Yeah.
As well as the ground level, it's really important to know that up to an accurate level. And you can use classified points, but still finding the right cross section in there, it has to be super fast, because as you could see in the presentation, there are lots of paths. Even for a small area of 100 by 100 meters, we already had more than 100,000 cross sections. So it's really important to be able to process these cross sections quickly. And for that, the tin was very efficient.
Well, and that was not the last question, because I also skipped the question of Balas. The focus of your project was on accuracy over computational efficiency. If you were to optimize your software, where would you begin? And that's really the last question, and then we move on.
Write it in C++.
yeah,
Because like half of our program right now is outputting files. Like for every single cross section, there needs to be outputted a file which needs to be inputted into the Knossos software. So if you just simply write it in C, then you can instantly input it into the Knossos software without having to output to a file. There might be ways of doing this in Python. I'm not a Python expert. I'm sure there is ways for doing this. So we didn't do that. So if you remove something like that, then you're already pretty much reducing the program down to half its runtime currently.
Super. Point has been noted. Thank you very much. I will then be the only one giving you the applause for your very nice presentation or video and the discussion that we had. Thank you very much. And then we will continue in a minute with the presentation by Tensing, combining GIS and natural language processing. So again, thank you very much, and we will be back in a minute.